These are the solutions to calculus homework number 28. These problems described here from the textbook. So starting with numbers 6 and 7, our task here is, given some function y of x, we want to graph the derivative of that function. So we'll start by figuring out where the zeros of that function are. So this is, of course, the points where the tangent line is horizontal. So we have a tangent line that's horizontal right here, and a tangent line that's horizontal right here. So in order to graph the derivative, we know that these points are going to be the locations where, let's use a lighter color, where the derivative has a 0 value. So those are these 2 points. Then between those 2 points, we can estimate a slope, and that will give us our value for the derivative. So for instance, right here in the center, if we sketch a tangent line, so just kind of approximate this, we see that we have a slope that is approximately positive 3. And that means that at this point, where I sketch my tangent line, we have a value that is about 3. Similarly, over here, we can do the same thing. We can say, okay, about right here in the middle of this section, we have, again, a slope that is magnitude 3, but this time negative. So at that midpoint, we have a value of negative 3. And you can kind of see where this is going. Over here, we have another tangent line. So we'll just sketch it right down the middle of this section. And it appears that right here, we again have a slope of about negative 3. So what does this look like? Well, without too much guessing, we can say that the slope looks something like this. And then it goes back towards 0. It looks like it stops about right there. So this right here is my y prime of x, the derivative of y of x. For number 7, we have a similar situation where we have something that has a 0 slope about right here, a 0 slope about right here, and a 0 slope down here. So that means that the derivative y prime of x is going to be 0 at those locations. So 0 here, 0 here, and 0 somewhere over here. So looking at our graph, we're just going to be doing some sketching here because this is a little bit more difficult. We have a very negative slope that gets close to 0 about right here. So what we can do is we can say something that essentially looks like this up to this point. And then, actually we can curve that a little bit more. And then is slightly positive for a second because you see it peak below. And then it dips down, and we have a negative slope again. So we have a negative slope up until this point. So if I look right in the middle of this line, I can approximate with a tangent line the slope, which appears to be about negative 3. So this will go dip down to about negative 3, and then come back up. And then we have a positive slope. And so the positive slope, again, we can approximate is about positive 3. And so it'll go up to somewhere around here, positive 3. And so our derivative sketch would look something like this. So this purple line is our derivative of the blue function y of x. For questions 13 through 16, or 13, 15, and 16, all we're doing is sketching f prime of x, which is the derivative. The important part here is that we have the same alignment with our original function. So for this particular function, we have a point that is of interest right here where our slope is 0. And so that translates to an f prime of x that has 0 value at x equals 2. To the left of this point, we have a value of f prime of x that is equal to the slope, and it is negative. To the right of this, we have a slope that is positive. It's increasing. So that means the value of my f prime of x has to be negative to the left of this and positive to the right of this. And so that function will look something like this. Because let me make that a little straighter. Because my f prime of x should just be linear. If this is a parabola, we should end up with a linear f prime of x. Now question 15 is a little more complicated. We have several points where the slope is 0. We have a tangent line of 0 in the center, and then on the left, and on the right. So, at these exact points, my f prime of x should be 0. At this point, that aligned here, at the center, at the origin, and also right here. Then, between each of these 0 values, we will look at the sign of the slope. So on the left-hand side, we have a negative slope up until the 0 point. Then we have a positive slope in between these two zeros, a negative slope here, and pardon me, I ran out of room, and a positive slope at the far right end. So what will this end up looking like? Well, we will have a negative value for f prime of x up until this 0. So we'll do something like this. And then we have a positive value. We can actually make this a little bit bigger. Positive value in the center. Then a negative value for these. And then a positive value at the end. So it appears that f prime of x has something to do with, given the number of bumps, x to the 4th, so this is a quartic function, which should give us an f prime of x that is cubic. So it's an odd function, or it has 3 roots. So we can always double check ourselves because we know that the order of the function, in this case 4, will go down by 1 when we're talking about the derivative. For numbers 16 and 17, we have a little bit simpler now. So we only have one location, it appears, where the slope is approximately 0, and that is right here at the origin. So we will have a value of 0 for our f prime of x right at the origin. To the left of this, we have a positive slope, and to the right of this, we have a positive slope as well. Well, what does that mean? What that means is we need to think a little bit harder, because f of x here is very obviously an odd function. Because it's odd, that means we will probably assume that this is an x cubed function, which means that since our derivative is positive on both sides, we actually end up with something that looks like a parabola for the derivative. Now, why does that make sense? Well, if you look really closely at the values for the slope, they're very steep far away from the origin, and they get less steep as you get close to the origin. So what that tells us is that the value for f prime of x is very high. The slope is very high far away from the origin and gets steadily closer. Then the mirror of that is true as you move to the right. The slope is very, very shallow, close to the origin, and it gets steeper as you get far away from the origin, which means the value of f prime of x should be getting larger. Now for 17, we have a really interesting situation because at this exact point, the slope is undefined, right? At this exact point, the slope is undefined because we would call this a cusp. You don't really have a slope value when it comes to a point. So, on the left-hand side of this interesting point, we have a positive and constant slope. On the right-hand side, we have a negative and constant slope. So I'm actually going to go in and say, this is f prime of x, and say that it is constant. And over here, we have a constant. And so what does our derivative look like? Well, we will have... So actually, let's sketch a new set of axes for this because we don't have any negative values. So we have a positive x and y axis. Maybe we'll call this f of x. We'll call it y. And it is going to be positive and constant for some amount of time. And then it is undefined. So you have a vertical asymptote, and then a negative and constant value. So this right here is our graph of f prime of x. For question 20, we're given a table of x and g of x values. And we are asked, for what value of x does the derivative of g appear to be closest to 3? So we want to see when the instantaneous rate of change is closest to 3. So for instance, if I look from these first 2 points, I see that the change, or the average rate of change, so let's make a little addition to our table, between these 2 points is plus 1. For the next 2 points, we have plus 0.6. For the next 2, 0.4. For the next 2, 0.6 again. For the next 2 points, 1.4. For these 2 points, we have 2.6. And for the final 2 points, we have approximately 2. So, for what value of x does the derivative appear to be closest to 3? Well, we can see from just the average rate of change that the average rate of change between these 2 points is actually the closest to 3. So we have to assume that somewhere near either 5.2 or 5.7, we will have our closest derivative value to 3. So the real question is, which side should it be on? Well, we see that it decreases to either side, but it seems to decrease less to the right. So we should say that somewhere between 5.7 and 6.2 is the only possible time to have a g prime of x close to 3. Now we should be a little bit more specific because it does say what value of x does it appear. So the real question is, how do we want to estimate this? Well, 0.5 to the left gives us a change of 1.4. 0.5 to the right gives us a change of 2. I'm sorry, 0.5 to the left gives us a change of 2.6. 0.5 to the right gives us a change of 2. So somewhere around this 5.7 is what we want. I guess we should broaden this a tiny bit. So, in this interval, the real question is, which side are we going to stay on? So we're going to lean a little bit to the right side because you have a smaller decrease. So that would imply that our increase of 3 is probably somewhere between the 5.2 and 5.7 mark. And so what does that do for us? Well, we can just, at this point, estimate. We'll probably be a little bit closer to the 5.7. And so a good estimate might be, well, first off, we'll say estimate between 5.2 and 5.7. And we might estimate a good value of about 5.5. That would be my estimate. You can feel free to estimate slightly differently. Questions 22 and 23 ask us to match a function with a graph of its derivative. Now, instead, I am just going to simply sketch the derivative. So for this first one, we see that the slope is just a constant and negative value. So I'm going to sketch down that the slope is negative and constant, which means that my f prime of x would be negative and constant. So I should end up with something that looks like a horizontal line with a negative value. For 23, I have a situation where my slope, or my tangent line, is 0, somewhere to the right of the y-axis, and it is negative, so here's my 0, it is negative to the right and positive to the left. So I will have a line that has a positive value to the left and a negative value to the right, which will look something like that. So if we go to our choices of graph, and you want to know, the graph that corresponds with the derivative of 22 is graph IV, or 4. And the graph that corresponds with 23 is graph Roman numeral 2. For number 28, we are given a function f of x equal to the natural log of x. And we want to use small intervals to estimate the derivative at x equals 1, x equals 2, x equals 3, x equals 4, and x equals 5. So, in order to do this, I'm actually going to use my calculator, and I'm really going to use my symmetric difference formula. And this is the formula that should be stored in your calculator. So this is stored in y2. So if I go in and plug in, actually, let's not call it plug, let's call it enter. If we enter ln of x for our y1, we can just use either a list or we can use the vars menu to find all of these different derivative values. So go ahead and do that now. I will pause for a second and actually do this myself. So you will notice that you get several errors when you go into your table. That's because the argument of a natural log cannot be 0 or less. So when we plug these in, we actually see the following for our derivative values. So for f prime of 1, you get a derivative value of 1. For f prime of 2, you get a derivative value of 0.5. Then 0.333, and so on, 0.25, and 0.2. Now B says, use your answers to estimate a formula for the derivative. Well, if I look at these, I kind of see a little bit of a trend, and hopefully you do as well. Because what it appears is that each one of these is really just equal to 1 over the x value that I plugged in, right? Because f prime of 1 would be 1 over 1, which is 1. F prime of 2 would be 1 over 2, which is 1/2. F prime of 3, 1/3, 4, 1/4, 1/5, and so on and so on. Hopefully you notice this pattern yourself, but if not, that's perfectly fine. For question number 30, we are going to be matching some descriptions to the graphs. So these descriptions always deal with the derivative. So let's go through this one at a time. So for A, we have a situation where the derivative at 1 is positive. So the derivative at 1 is positive implies that the slope at x equals 1 is positive. Then the value for this is always decreasing. So the slope at x equals 1 is positive, and the slope is decreasing. So if we go through our graphs, we see for graph 1 that the slope is actually negative. So this one is right out. For 2, it appears that the slope is increasing. And the reason why we say that, even though it looks like the value here is decreasing, is because if you think about it, the slope up until about right here, so this is about where the tangent line is horizontal, the slope is negative and then it turns positive. And that's okay, because that means that f prime was negative and is going positive. So this actually implies that our slope is increasing the entire time. So between these two, we really don't quite have an answer. So let's continue on. Number 3, we see that up until about this point, so this is our 0, we have a positive slope and then it is negative. So this is decreasing the entire time because this slope is positive and is getting more and more negative. Then at x equals 1, we see that our slope is positive. So that means that A matches with graph 3. So we'll write it in both locations. Now, moving on. B says f prime of 1 is greater than 0. So it's the same thing for the slope, except that now it's increasing. So if we know that this is A, there's a good chance that number 4 is B. So let's double check. So about right here at the origin, we have a slope of 0. To the left of that, we have a positive slope, and to the right, we have a negative slope. So this seems to be always decreasing again, because our slope is positive and getting more and more negative, even though our slope at x equals 1 is negative. That doesn't seem to help at all. So the only other location where our slope was positive at x equals 1 is in graph number 2. And so let's double check. Is f prime always increasing? Well, it was negative and it's becoming more and more positive, so yes. Graph number 2 matches with description B. For C, we want a negative slope at x equals 1, and we want in this case to always have a decreasing slope. So how does that help us? Well, at approximately this location, we have 0 slope, which is negative. Then it is increasing to be positive, so this is not increasing. Down here, we said that our slope was always decreasing. It's going from positive to become more and more negative, and we have a negative slope at x equals 1. So Roman numeral 4 matches with description C, which by process of elimination brings us that description D will go with Roman numeral 1, but let's double check. So we have f prime of 1 is less than 0, which means our slope is negative at 1, and it is. And f prime is always increasing. So our slope is negative and it is getting more and more positive. So sure enough, Roman numeral 1 goes with description D.